We continue to analyze the graphs of functions. This is part 2. And the first thing before we actually get into some analysis is defining local maximums and minimums. Now there's a piece of terminology here that you need to be aware of. I will use the word local for what we're about to discuss. You will find out that in the literature, in some books, the word relative is used instead. They are interchangeable terms. I like the word local for a number of reasons, and you'll see why. But if you see relative, it means exactly the same thing. Well, let's suppose we have a graph with a lot of ups and downs, something like that, say. And let's just run an x-axis through there. Now, just by looking at this picture, you see that there are points like this one up here, which would be a maximum for the entire curve. The curve apparently never gets above this point. Here, the curve never seems to get below, but in addition to both of those, there are all these other little ups and downs. For example, this point here is a maximum as long as I stay in some sort of locality around this point. If I go too far, other points get higher. But in this locality, this is a high point, a so-called local maximum. Then, for example, this point here would be a local minimum. And again, if I stay in some open interval very close to this point, all the points around it will be above it. So this will be a minimum for that small locality. And there are other ones. Here's another place that might be a local maximum. Here's a point that would be a local minimum, and so on. So not only do we want to find the biggest maximum and the smallest minimum, we want to find all the other ones in between because they tell us parts of this curve. They tell us interesting things about the curve. So maximums and minimums in some limited locality, sometimes called a vicinity of a point. That's what we're going to be interested in examining. And that's what we're going to end up calling local maximums and local minimums. So let's just go ahead and do that. Definition. F, a function, has a, and we'll call this local maximum. So that's the term being defined here. At a point x naught, if, well, what does it mean to be a maximum at that point? It means that all the points nearby have heights that are less than the height at that point, which is to say, f of x naught, the height at x naught, is greater than or equal to f of x. Maybe not everywhere, but in some locality around x naught. So that would be for all x in some open interval, that's what we mean by locality, in some open interval of x naught. And so if we draw ourselves a picture here to see what's going on, perhaps we have an open interval here, and we pick some point in here, x naught, and there is a maximum that occurs just above x naught. That would be, of course, at a height f of x naught. And that would be what we call a local maximum, because for this locality at least, all the other heights of the points are smaller or equal to. There could actually be a point that's the same height, but it will never get higher than this one. That is the local maximum. Likewise, we can define local minimum in exactly the same way. A local minimum at x naught happens if, well, this time f of x naught, we don't want greater than or equal to everything, but less than or equal to everything nearby. So this would be, again, for all x in some, the locality is an open interval of x naught. And just one more piece of information, a terminology. We will say local extremum if we want to talk about either one of these. Rather than say local maximums and minimums, we will say local extremum to mean one or the other. So this means either of the ones above. So there's the terminology. And you can see it's very natural. In fact, let me draw a picture here for the local minimum also. We have this open interval. We have some point x naught here. Then if we have a local minimum above x naught, then this height, f of x naught, is lower than the heights of all the nearby points. So those are the basic ideas for local maximum and minimum. We want to know how to find these. That's our goal here. We want to use calculus to do that. So let's observe a couple of kinds of minimums and maximums and see if we can deduce how the calculus appears. Here's a picture. Suppose this is x naught, and above x naught there is a maximum that comes from a curve that curves up like that. So there is a maximum point. Now let's also look at possibly at another point x naught, a minimum that comes from another one that is a nice smooth curve. Now in both of these you can see that the function is defined at these points and apparently has a tangent line there. In other words, there is a derivative at x naught in both of these, and the derivative appears to be 0 because the slope of the tangent line appears to be horizontal. This is the nice situation and very often happens. However, these are also legitimate maximums and minimums. Here is a maximum, and likewise, this might be a minimum. Maybe give it a little curve there. Now, you see what's different about these. In these, the derivative at x naught does not exist. There's no derivative where there are corners on the curve. And so this is a case where the derivative doesn't exist, and yet we have local max and a local min. Likewise here, the derivative does exist and happens to be 0, and we have a local max and a local min. So don't limit yourselves to this. Remember that this case can also occur. So let's write some things down here. Definition. A point x naught in the domain of the function f is, and here's one definition, it's called a critical point. X naught is called a critical point for the function f if one of two things happens. Either f prime at x naught is 0, which is like these cases, or f prime at x naught doesn't exist, which is like these cases. So points that lead you to these situations, x naughts that lead you to these situations, are called critical points for the function. Now, the ones on the left are particularly nice, so they're going to have a special name of their own. A stationary point for f. And you can see why we're going to call it a stationary point, because if you imagine putting a ball up here on this tangent line, it's not going to go anywhere. It's going to remain stationary. Same thing here, because the line is horizontal. A stationary point for f happens if the derivative at x naught is simply 0. So what we've got here is a subcategory. And it's a subcategory of critical points. So if you want to have all the points where the derivative is 0 or doesn't exist, you'd call them critical points. The ones where the derivative is 0 are called stationary points. And that just makes things a little easier to talk about. So with those definitions in mind, we have a theorem here. Let us suppose we have a function, let f be defined on I, an interval, I stands for intervals here, open, and it contains, so this containing x naught. So the picture is we have an open interval of some kind, and somewhere in here is a point x naught. And the function is defined on that entire interval. Here's what we want to say. F has a local max or min, I guess I could have said local extremum here, at x naught. That is going to imply, so if it does have a local minimum or maximum at x naught, that means that the point x naught must be one of those critical points. Must be a critical point of f. And just to put the definition here to remember it, meaning f prime of x naught is 0 or doesn't exist. So if you have a local maximum or minimum on your graph, then the point x naught above which or below which it occurs is a critical point. But we'll see that the reverse direction doesn't work. But we'll see that x naught, a critical point of some function f, that does not go backwards and imply that f has a local, and let's use the word extremum here just to practice it, local extremum at x naught. So it is not true that this theorem works in reverse, and many theorems are like that. They only work in one direction. If you have a local max or min, you're guaranteed that the point at which it occurs is a critical point. But there may be more critical points than there are local maxes and mins, so the backwards direction here doesn't work. So when you have critical points, what have you got? What have you got? You've got candidates. That's a nice way to say it. Candidates for local max mins. All right? You don't necessarily have a max and a min, but you have candidates which at least narrows the field. It's time to put the calculus to use here. We will first look at the first derivative and talk about something called the first derivative test for local maximums and minimums. Observe the following. And from these pictures, we will be able to deduce the first derivative test. Now, in all of these situations, I'll just mention that f is continuous, so there are no breaks in it, and it'll be continuous at the critical point, x naught. Then, let's first look at a local max situation. Suppose we have, at the point x naught, a local max occurring above x naught. And it is not just any local max, it's a local max where the derivative is equal to 0 at x naught. Now notice in this picture that to the left we have the derivative greater than 0 because that's what we use to indicate when the function is increasing. To the right the derivative is less than 0 because the function is decreasing. The other case of a local maximum, you know, is one where the first derivative does not exist at all. And so we might have a picture something like this. In this case, we have f prime undefined. That's a short way to say that. It doesn't exist there. On the left, we have f prime greater than 0 because the function is increasing. And we have f prime less than 0 on the right because the function is decreasing. Notice that for a local max, the function is increasing and decreasing and changing from increasing to decreasing as you go from left to right. Let us look at a local minimum case. In a local minimum case, if this is x naught, we have perhaps a picture like this. Here, this is the case where f prime is equal to 0 at x naught. And at the left, we have f prime. It's decreasing, so that's less than 0. And on the right, we have f prime greater than 0 as it increases on the right. The same situation can occur if we have a function that has no derivative at x naught. So this is where f prime is undefined. But on the left, you notice that we have f prime less than 0 because it's decreasing. And on the right, we have f prime greater than 0 because it's increasing. So in both the local max and the local min case, the derivative is changing sign from positive to negative or negative to positive in these cases. There is one other case in which you neither get a local minimum nor a local maximum. And here are some pictures to illustrate that situation. If this is x naught, you might have something that looks like this, where here f prime is equal to 0. There is, in fact, a derivative at this point in the center. On the left, you have f prime greater than 0 because the function is increasing. But notice that on the right, you still have f prime greater than 0. The function continues to increase. So it does not change its direction of increase and decrease. It's always in one direction. Likewise, we can have the other case, if this is x naught, and maybe something like this might occur, where f prime is undefined here. And the reason is because it would be a vertical tangent, and so the slope of the derivative would be undefined. But notice that f prime is less than 0, decreasing on the left, and it continues to decrease on the right. It does not change. So it seems like in order to get a local max or a local min, the derivative must change its sign as you pass over one of these critical points. So that seems to be the idea here. And in fact, that's enshrined in what's called the first derivative test. So using these observations, I won't write out the test because we've already seen how it works, but we'll examine it in examples. Using these observations, we have what's called the first derivative test, because it uses the first derivative, of course. The first derivative test. And when people write down these tests, they very often don't say what they're testing for, so I always like to write the full name. The first derivative test for local, and let's go ahead and practice that other name, extrema. That's the plural of extremum. So the first derivative test for local extrema. And it's best to just go ahead and show this by example. So let's take a function here. F of x equals x squared minus 3 times e to the x. And what we want to do is produce a graph. So let's go through the process and see if we can find the local extrema using what we just learned in this first derivative test. So we'll need the first derivative, of course. So the first derivative, well, this is a product. So let's use the product rule. We'll leave the first thing alone, x squared minus 3 times the derivative of the second. But of course, the derivative of e to the x is just e to the x. Then we'll take e to the x times the derivative of the first, which is 2x. And that nicely factors. We can pull out e to the x. We're left with x squared plus 2x minus 3, which factors into e to the x times x minus 1, x plus 3. And it's easy to see that this is 0 for x equal, let's see, 1 here and minus 3 here. So those are the numbers that will make the first derivative 0. So if we build our usual chart here with minus 3 and a 1, if we go way below minus 3 to minus a million, and we put that in here, this will be negative. This will also be negative. So the product will be positive. F prime will be greater than 0. And I didn't mention it, but e to the x, of course, is always positive. So this becomes positive. That means the original function is increasing, which means we're going up. Here between minus 3 and 1 is a nice number, 0. Putting 0 in here, we get a negative times a positive. That makes this negative. So the derivative is negative, which tells me the original function is decreasing or going down. And then if we put a million in here, we see that this is going to be positive. So the derivative is positive, the function is increasing, and then goes up like that. We see that between the first two here, since we go from increasing to decreasing, that at minus 3 we have a local max, and between decreasing to increasing at 1, we have a local min. If you then graph this function, you can use your graphing calculator if you like, you get something that looks like this. Goes up like that, down here like this, and then up. At minus 3 is where it has the local max that we predicted here, and at 1 is where we have the local min that we predicted here. And so you can see, this is 1, you can see that this test is a very easy way of finding where it has local maxes and mins. This function only has one of each, but there could be many, and this test will allow you to find them all. Well, where there's a first derivative test for local maximums and minimums, you might expect there's a second derivative test, and you'd be right. The second derivative test, well, if we have two tests, which one should we use? Well, it really doesn't matter, except that there's some rules of thumb that will allow you to pick one that might be a little more computationally easier than the other. So, the second derivative test is, of course, an alternative to the first derivative test. And you can use either one, but a good rule of thumb is use only, so use the second derivative test, that is, only when the second derivative is easy to calculate. That makes sense. If the first derivative is easy and then the second derivative becomes very difficult, you probably don't want to go in this direction, just go with the first derivative test. However, if the second derivative is going to drop right out, then go ahead and use this test. And the reason that the second derivative test is nice is because instead of looking to the left and the right of x naught, which is what you have to do for the first derivative test, you examine what's happening on the left and on the right, you just look at, or just look directly at x naught. What is happening at x naught is all that is needed if you are using the second derivative test. Let me show you why that's true. Observe. We will assume here that f double prime at x naught exists so that we can have a second derivative test. And of course, that means immediately, thus, f prime at x naught must exist. It must exist previously. Before you can get to the second derivative, you must have the first derivative. So here are the two pictures I want to look at. In this picture, here is my x naught point, and I have a curve like this where the first derivative exists, and of course, if this is a local minimum, the first derivative is going to be 0 there. And here, the second derivative, which represents concavity, and since this is always concave up, this means the second derivative must be positive. Likewise, if we have here a curve with a first derivative existing above a point x naught that gives me a local maximum, notice here that the second derivative, because this is concave down, must be less than 0 or negative at x naught. So if we have a first derivative, as we do here, and there is a local max or min, which means the first derivative is 0, then we see that by looking at the second derivative alone, we can discover whether we have an upward going curve, which makes that point a minimum, or a downward going curve, which makes this point a maximum. And that's the entire key to the second derivative test. And it goes like this. Suppose you have f prime at x naught is equal to 0, so that means you have a point where there might be a local max or min, and you know that the second derivative at that point is greater than 0, so it's concave up. That implies that the original function has a local minimum at x naught. And the picture you want to keep in mind is something like this. This line represents the first derivative being 0, a tangent having a slope of 0, horizontal tangent. And this upward curve means the function's concave up there, which forces this to be a local minimum. Makes perfectly good sense. Then likewise, if the first derivative is 0 and you have the second derivative being less than 0, that implies that f has a local max at x naught. So in this case, a picture something like this would be appropriate. Finally, there's the last case. If you have 0 for both of them, both the first derivative and the second derivative are 0 at the point x naught, then you get no conclusion. This is inconclusive. You'll have to try something else if you want to learn what's happening at x naught. This is inconclusive, and just to show you that this actually happens, here's an example. If we have a curve like this, and I can actually give you one, take f of x equals x cubed, for example, you see here that at x naught equals 0, we have a horizontal tangent, which says the first derivative exists and equals 0, and the second derivative is 0, and you see in this case there's no local max or min. This is to have a point here where it flattens out for a moment but continues to rise on both sides. Let's look at an example to explore this second derivative test. Here is the function f of x equals 3x to the fifth minus 5x cubed. We want to find the local max mins here. And since we're in the section on the second derivative test, we'll use the second derivative test, of course. So here is our solution. To get to the second derivative, we have to pass through the first derivative. So the first derivative here is going to be 15x to the fourth minus 15x squared. That factors, let's see, 15x squared comes out, which leaves me with x squared minus 1. That in turn factors into 15x squared times x minus 1 times x plus 1. And this expression is going to be 0 for, let's see, x equals 0, that would be the first factor, x equal 1, the second factor, and x equal minus 1, the third factor. These are what we've been calling stationary points, points where the first derivative is 0. Let us also compute the second derivative. And the second derivative, I'll work from this expression. I've said this before. If you have a first derivative that you may simplify for some reason, sometimes finding the second derivative, you just work with the first unsimplified expression. And that's easier here. So I take the derivative here. I get 60x cubed minus 30x. That factors. I get 30x I can pull out. And I'm left with 2x squared minus 1. Now, I'm not going to do anything further here because I don't care where this goes to 0. What I want to do is use this second derivative as a tool to examine these three stationary points to see if there are points where they are local maximums or minimums. And so what I'll do is take these points, and then I will apply the second derivative to them, f double prime of 0, f double prime of 1, and f double prime of minus 1, and then see what I get. If I put 0 in to this expression, I get 0, which implies there's no conclusion. Meaning at the point x equals 0, I cannot tell from this test what's happening there. At 1, if I put 1 in here, I get 30 times 2 minus 1 is 1, so this just becomes 30. 30 is greater than 0, so that implies I have concave up, which means I have this kind of a picture. And of course, that means I have a local minimum at 1. Finally, if I put minus 1 in, I get a minus 1 here. This becomes again 1, so this is minus 30, which is less than 0. That implies I have concave down, which from the picture is immediate. I have a local maximum at minus 1. So I've found out all of this using this second derivative test. And now let's go ahead and draw the graph so we can see what we've got here and verify that what we learned is really correct. So the original function is 3x to the fifth minus 5x cubed. Here is a picture that you can get from your calculator if you like. Goes something like this. Here and here, let's see, mark this point at minus 1, we have a local max. That's what we predicted would be there. Here at 1, we have a local min, which we also predicted. And here in the middle, we have neither. We weren't able to tell anything from the test, and we can see from the picture that it's just decreasing on both sides, so it's not a local max and it's not a local minimum. So that is enough to give us an example to see how useful this second derivative test can be. Let's use the new tools we've developed, this first derivative test, second derivative test, and so on, to find out something about the graphs of our familiar functions, the polynomial functions. We use these enough that it's worthwhile taking a moment to just talk about these functions. Let's recall, first of all, some facts from algebra about polynomials that you may not remember. A root, which we'll just label by r here, a root r of a polynomial, and we'll name the polynomial, say, p of x, p for polynomial, has what's called multiplicity. So a root has multiplicity, and we'll use the letter m, which will be 1, 2, 3, and so on. If, here's how you tell, if x minus r to the m power divides into p of x, but the next power does not. X minus r to the m plus 1 power does not. So it is the highest power of x minus r that divides into p of x. That's the multiplicity of r. One more thing to remember from algebra about polynomials, and there'll be some more in a minute. Remember, if you mark the roots as r1 to rn, if these are the roots of a polynomial p, or p of x, of degree n, the polynomial of degree n will have n roots, then p of x can be always written as some constant, say a, times x minus the first root to some power, say k1, all the way down to x minus the last root to some power associated with it, kn. So polynomials can always be written that way and factored in that way. And of course, some of these roots could be complex numbers, but we won't be facing those situations. All right, so why did I mention multiplicity? What multiplicity tells you, multiplicity M, tells you about the graph of a polynomial. That's what we really want to know here, about the graph of p of x, our polynomial, at the root r, the x value r. Well, there are three cases. If M is an even multiplicity, that implies the following about the polynomial p of x at the root r. It is, the graph of this function is tangent to the x-axis there at r. It does not cross the x-axis at r, and it does not have an inflection point at r. So those are the things that you learn if the multiplicity of your root is even. If the multiplicity is odd and bigger than 1, we'll take 1 as a separate case in a minute. If the multiplicity is odd and bigger than 1, then here's what you know. The tangent to the x-axis for such a curve does occur. The curve is tangent to the x-axis at r. And in this case, it does cross. If the multiplicity is odd and greater than 1, it does cross the x-axis at r. And it does have an inflection point there. So an inflection point at r. So if it's odd and greater than 1, you do get an inflection point and you do cross. Finally, the special case m equal 1, if there is just a factor of x minus r as part of your polynomial, then the curve is not tangent to the x-axis at r. It does cross. That still holds true. It does cross the x-axis at r. And inflection point at r, well, who knows? Could be, could not be, it depends. Usually it will be no inflection point. But these are algebraic facts. And let me show you some pictures to set them in your mind. We haven't gotten to using the calculus yet, but here is a sequence of pictures that I hope will help. If m is even, you might have a curve that's like this. Notice that it's tangent at the x-axis, as was expected, and it does not cross. So variations on y equals x squared are going to have this kind of feature. If m is odd and m is greater than 1, then you might have this sort of a picture. Curve that comes up and does something like this. It is tangent. Here's the x-axis. It is tangent at the x-axis again. This point here is clearly an inflection point. And notice that it does cross. It crosses the x-axis. And finally, the m equal 1 case. In this case, we'll have a curve that just crosses. And that's pretty much all you can say about it. But at least if you have these in the back of your mind as tools to analyze the graph of a polynomial, they will help. Now, of course, these are not calculus. We're going to be getting to calculus in a moment. But let's just go ahead and put a few more of these polynomial graph facts. We do polynomials so often that it's worthwhile having these at your fingertips. So polynomial graph facts. The first one, and we'll suppose we have a polynomial p of x. The first is that the domain of the polynomial is all the real numbers. That is to say, everything. Polynomials are defined everywhere. Secondly, the polynomial p is not only defined everywhere, but it is continuous everywhere. So there are never any breaks in any polynomial whatsoever. Thirdly, the derivative of this polynomial exists everywhere. And what that means to the picture is that there are no corners, and there are no cusps, and other kinds of places where the derivative won't exist. There are no vertical tangents either. That would be a place where the derivative doesn't exist. That won't happen in a polynomial. If you take the limit of the polynomial and you go either to plus or minus infinity, what you end up with is either infinity or minus infinity. And that's because the polynomial has no asymptotes. No horizontal or vertical asymptotes. And which one it goes to, the plus or minus infinity, is going to depend on the degree of the polynomial and the plus or minus sign of the leading coefficient. But in any case, you will never have asymptotes, so you don't have to worry about those. And finally, here's one that's very interesting. If p has degree n, say, then you can say this about p. P has the following. At most n x-intercepts. So if it has degree n, it has at most n intercepts, n x-intercepts. And that's because the degree of p is equal to n. It will have at most n minus 1 local maxes or mins. Now here's where the calculus comes in. This is because the degree of the first derivative is always 1 less than the degree of the previous polynomial. That's going to be n minus 1. So that's only n minus 1 chances for the degree of p prime is n minus 1. There's only n minus 1 chances for this first derivative to be 0, and hence only that many chances for local maxes and mins. Finally, there are at most n minus 2 inflection points because these come from the second derivative. And that would be because the degree of p double prime is at most n minus 2. So there are the polynomial facts that really are mostly algebra, although these two here and do involve the notions of calculus. And let's see how those work in practice now. Suppose we have the following polynomial function, y equals x cubed minus 3x plus 2. What we want to do here is analyze and graph this function. So, to do an analysis, first of all, let's just look at the function itself before we do any calculus on it. This function can be written, we can factor this, and it's not something that's going to come to you immediately, so I'll just give this to you. X plus 2 times x minus 1 squared. With a little work, you could figure this out. This factors in this way. This is by algebra. Notice that this has multiplicity 1, and this root 1, because x minus 1 is squared, has multiplicity 2. So those multiplicities then have bearing on what happens to the graph of the function. If there's multiplicity 1, notice that the function's graph will cross at, let's see, minus 2. And it is not tangent at that point to the x-axis. Here, it doesn't cross because it's a second degree. This is multiplicity 2. It doesn't cross at the value 1 here, which is the root. And it is tangent to the x-axis. And another thing we can notice from this right away are the x-intercepts. So let's just go ahead and mark those down. That would be x equals minus 2 or 1, where these become 0. All right. Well, let's go ahead and use the calculus. If we take the derivative, let's go back to the original form for the derivative. That's easier. 3x squared minus 3, which factors into 3 and times x squared minus 1, which nicely factors again into 3 times x minus 1, x plus 1. We know that this is going to be 0 for x equal minus 1 or 1. These are stationary points, using our language here. These are stationary points for the curve. And finally, let's take the second derivative, which from this expression is easy. It's 6x. And 6x, of course, is 0 only for x equals 0. So we found that there are points here of interest for the graph. For the derivatives, -1, 1, and 0 are particularly important. And later on, we'll use the x-intercepts and use this information to make our graph. But first, let's go ahead and build a chart as we always do. Here's the first derivative for a reminder, 3 times x plus 1 times x minus 1. And the second derivative was just 6x. There are 3 points of interest here, so I'll mark them on my chart, -1, 0, and 1. The -1 and 1 are what affect the first derivative, so that's how I will need to mark there. And the 0 is what affects the second derivative. The first derivative, if I go very far below -1, this becomes negative. This becomes negative, and a negative times a negative is positive. So y prime is greater than 0, which means the original function y is increasing, and I'll put an arrow going up. Between -1 and 1, 0 is there. That's a nice number. So we put this in here. I see that this will be negative. So y prime is less than 0. That means the original function is decreasing or going down. And then above 1, these are both positive. So y prime is greater than 0. Y, the original function, is increasing and therefore going up. And also notice that here, because it's going up and then down, I immediately see that I have a local maximum. That's the first derivative test being acted out. And here, because it's down and then up, I see that I have a local minimum. This is also the first derivative test acting out. Then down here for the second derivative, if I'm below 0, I'm talking about negative numbers. That's going to make the second derivative, of course, negative. That means y is concave down. The original function is concave down to the left of 0. And then to the right of 0, the second derivative is positive. So y is concave up and looks something like that. And because there's a change of concavity, the point in the middle is an inflection point. And once again, this organized chart tells us everything we need to know about the function and using the first and the second derivative. Let us look at the graph here. The original function, remember, is x cubed minus 3x plus 2. Here is the picture, and it looks something like this. And crosses here at minus 2, that was one of the x-intercepts. Has a local max at minus 1, we discovered. At 0, has an inflection point. Let's mark that. At 1, it has a local minimum. And let's see, it is also tangent. Notice that the x-axis here is tangent at this point, which we learned earlier. And from the graph chart that we built, we were going up, we were then going down, and then going up again. Here we were concave down and then concave up. All of that was reflected in that previous chart, which is the reason for doing these charts, so we can learn about the graphs of such functions. I hope you enjoyed that. Once again, some exercises. First, we'll look at a nice polynomial, x to the fourth minus 12x cubed. And as we've been doing, we'll try and find everything about this. So we'll find where this function f is, let's see, increasing or decreasing, concave, up or down, has inflection points, if it has inflection points at all, local maxes and mins, and finally, last but not least, we want to graph this function. So that's your task. Go ahead and give that one a try. Let's see what we can do with this function. First of all, let's write it out again. F of x equals x to the fourth minus 12x cubed. And of course, I'm going to want to work with this. So the very first thing I notice is I can factor it. So I'm going to go ahead and do that. And I'll pull out x cubed and multiply that by x minus 12. Now, based on what I know about multiplicity of factors in a polynomial, I can say this. For x cubed, since it is an odd multiplicity greater than 1, that means the curve f is going to cross the x-axis. It is going to be tangent to the x-axis at that point where it crosses, and this point will be an inflection point. So we'll have to check that later, but that's what we learn from the multiplicity of the factors here. And for this factor, since it is a power of 1, the multiplicity is 1, it will cross, and let's see, it'll cross at 12, and it will not be tangent because it is the power 1, so not be tangent to the x-axis. Okay, that's strictly from the algebra. Now we want to start bringing in the calculus. The very first thing we'll need to do is to take the derivative. So let's go ahead and do that. The derivative of x to the fourth is 4x cubed. 12x cubed has a derivative 36x squared. Again, there's a lot to factor out of that. I can pull a 4x squared, and I'm left with an x minus 9. This now be useful for us to know where this is 0. This will be 0 for, let's see, it'll be 0 for x equals 0, the first expression, the first factor, and it'll be 0 also when x is equal to 9. And these, of course, are what we've been calling stationary points. They're critical points, but they're, in fact, more specifically stationary points. All right. We need the second derivative also, so let's do that. And I will use this first form because it's easier to deal with here. Let's see, I'll have 12x squared minus 72x. And if I factor that, I get 12x times x minus 6. This expression is going to be 0 for, let's see, it'll be 0 for x equals 0 again, and for x equals 6. Okay, I have the first two derivatives, and now I can go ahead and create the chart as I always do. So let me rewrite those derivatives here. 4x squared times x minus 9, and the second derivative, 12x times x minus 6. The numbers that turned up in these three that were of interest are the 0, the 6, and the 9. And again, I'm not putting these with any reference to where they actually appear on the number line. I'm just going ahead and putting them in correct order. So for the first derivative, it was the 0 and the 9 that mattered. So let me mark those. So I'll have a strip here to deal with the first derivative. The second derivative, it was the 0 and the 6 that mattered. So I'll extend those down here. And then I'll be prepared to talk about the second derivative. So let's go back up to this strip and talk about the first derivative. Below 0, I want to know what sign, what plus or minus sign the first derivative is. Well, if I'm below 0, the first thing I should notice is that 4x squared here is always going to be positive as long as the x isn't 0. So this is not going to affect the plus or minus sign. The x minus 9 is all that I need to look at. And if I'm below 0, that's negative, so this is negative, which means the original function is decreasing and hence going downward. Between 0 and 9, I can pick a nice number, say 1, and I put that in here. Again, this first expression will not affect anything, so it's just 1 minus 9. And again, that's negative. That's interesting. So f is decreasing still. So it's decreasing in both these parts. If I go above 9, this is certainly going to be positive. So the first derivative becomes positive. The function is then increasing and hence going up. From all of this, I see that between these two at 9, I'm going down and then going up. This must be a local minimum based on what we studied earlier. All right, in this strip, I want to look at the second derivative's values. So if I'm below 0, looking up here to the second derivative, this first expression here will be negative, and this will also be negative. Negative times negative is positive, which means that the second derivative is greater than 0. That tells me that the original function is concave up with something like that. If I'm between 0 and 6 with another easy number like 1, for example, this is positive, this is negative, so that makes the second derivative negative. So f is concave down here and looks something like that. And then one more section here between 6 and infinity. So I just put a very large number in there. Clearly that makes that positive. So the second derivative is positive. That says that the original function f is concave up and looks something like that. And I see there's a change of concavity here and one here, so these two are, therefore, by definition, inflection points. All right, I now have the chart all put together, and I'm ready to draw a picture using this information. And I'll have this to refer back to as I need it. So the final step in this problem is to produce a graph. Here is the original function. It's always good to remind ourselves. X to the fourth minus 12x cubed. And here is a picture. I'll draw this freehand, of course. You could do this on a calculator, perhaps a little more accurately, but it looks something like this. It'll come down here and be tangent at the origin and then come up like this. So this is 0. The point where it changes its concavity here from down to up, we recognize happens at 6. This point down here, which is the local minimum, we know happens at 9. It crosses here at 12. In fact, I'll mark that just to remind ourselves. And just to get a sense of the scale here, let me mark a few numbers on here. The 6 takes us down to minus 1296, so it's quite a ways. The 9 takes us even further to minus 2187. In case you're trying to graph this yourself, you know what kind of window to look at. Now the 0 point here is an inflection point, and we learned that not only from the algebra, but we also verified it with the calculus. So this is an inflection point. It is a point where the curve is tangent and where it crosses. All of this we verified earlier. This point here, as I've already mentioned, is an inflection point. And of course, this is a local minimum. And we can see that the curve goes down from here all the way to the local minimum and then goes up exactly as we found in our chart of information. And so we've got a pretty good idea that this is correct. We see that it's concave down and then concave up and then concave, or concave up and then down and then up. And that's exactly what the curve says and what our chart said earlier. So I hope that's what you ended up with when you finish this problem. Let's look at a second one. Suppose our function now, we'll do one with the exponential in it. F of x equals x squared times e to the x. Again, we want to find everything. So find where f is, and I'll make the list once again. Increasing, decreasing, concave up, down. Eventually you'll just have this memorized. Inflection points, local max mins, or local extrema. Let's use that just to practice it, local extrema. And, of course, produce a graph. So that's your task now. Our function, x squared times e to the x. First, let's gather our tools together, the first being the first derivative. This is a product, so we'll need the product rule to begin with. That's x squared times the derivative of e to the x, which, of course, is just e to the x, plus e to the x left alone times the derivative of x squared, which is 2x. We can certainly factor some things out of this. Let's see, we can pull the x and the e to the x out, leaving us with x plus 2. Notice here, and this will always be true, that e to the x is positive, always positive. That means when we start looking at where this is positive or negative later, it won't matter what e to the x is because that's always positive. Then where does this first derivative equal 0? Well, it's 0 for, let's see here, 0 for this x when x is 0 and when x is minus 2. These again are examples of stationary points, points where the first derivative is 0. All right. We need the second derivative, and in this case, I think I'll use the second form. Now, I've got a product of three things, so what I'll do is I'll lump it. I'll keep the first two things together as I work my way through, just for convenience. So I'll take x times e to the x and leave it alone, times the derivative of x plus 2, which is 1. Then I will add to that x plus 2 times the derivative of x times e to the x, which is a product, so I'll need the product rule. So it's x times the derivative of e to the x, which is just e to the x, plus e to the x times the derivative of x, which is just 1. So all of that will simplify. Let's see, I can pull an e to the x out of all this, and I have x plus, what's left? X plus 2 times x plus 1. If I multiply this out, I'll have x squared plus 3x plus 2. And then if I recombine everything, e to the x times x squared plus 4x plus 2. Now, this won't factor into nice factors. It does factor, and in fact, we can find out what those factors are because we're interested in where the second derivative is 0. So it'll be 0, 4, and I'll let you do this yourself. X equals, let's see, minus 2 minus square root of 2. That will come from using the quadratic formula here. Or x equals minus 2 plus square root of 2. Now, since we'll be looking at a chart later on, let me approximate these so we have an idea what they are. This is approximately minus 3.41, and the other one is approximately minus 0.59. That'll just give a reference for us when we're graphing these. And remember again, in the second derivative, as in the first, e to the x is always positive, so that will not affect the plus or minus sign. All right, let's go ahead and put together a chart here. Let me repeat the derivatives so I'll remember them. X e to the x times x plus 2 is the first derivative. The second derivative is e to the x times x squared plus 4x plus 2. There were 4 numbers that just turned up, and let's mark those down. This is minus 2 minus square root of 2. The next one up was minus 2. The next one is minus 2 plus the square root of 2. And then the last one was 0. Now remember, this first one is approximately minus 3.41. This third one here is approximately minus 0.59. And so when I pick numbers in here to make my judgments, I will have a sense of where I should be picking them. Let's see now. For the first derivative, it was 0 and minus 2 that mattered. So if I mark this down like this, I can deal with the first derivative in that first horizontal strip. And then for the second derivative, there were 2 numbers, these 2 numbers here, and those will be numbers that will give me my divisions down here. All right, back up here. Let us find out what the first derivative is in this first region below minus 2. In this first region, if I'm below minus 2, this is going to be negative, then this will also be negative, so the product will be positive, and the first derivative is positive. So f is increasing in this, the original function f is increasing, which means it's going up in this region. Between minus 2 and 0, I can pick an easy number like minus 1. And I put that in the first derivative. I get a negative here. Here I get a positive. So the product gives me a negative first derivative. So f is decreasing here and therefore going downward. And then above 0, I can pick a very large number like a million. Certainly this will be positive. F prime is greater than 0. F is increasing and hence going up. And by looking just at this line, I use my first derivative test, which says if you go up on the left and down on the right, this point here must be a local max. So that's easy. You can read it right off the chart. And if it's going down and then going up, and the function, of course, is defined there, this must be a local min. So that's a convenience. Let us now look down here and find out what we can learn about the second derivative. Below this number, minus 3.41, let's go to some number like minus a million. Look at the second derivative, ignore the e to the x because it's always positive. If I go down to minus a million, it's going to be dominated by this squared term. All the rest of these won't matter in the end. So since it's squared, it will be positive. So the second derivative is positive. That says the original function is concave up, which looks something like that. In this region here, I can find a number to choose if I want, maybe minus 1, that's in there. And if I put minus 1 in here, I'm going to see I get 1 plus 2 is 3 minus 4, so that's negative. That makes the second derivative negative. F is then concave down, and hence looks something like that. And finally, if we go up here above this number to a very, very large number, say any positive number, this will be positive. So the second derivative is positive. F is concave up, and looks something like that. Since the function is defined everywhere, and these are both changes of concavity, these are therefore inflection points. So again, we've gathered all of the information we need, and we're ready to pull it together into a graph that's very specific. Here's the graph now, and the original function, let me write that again, is x squared e to the x. And here is the picture you end up with. Again, you can do this yourself on a calculator or computer program. You'll have something that looks like this. So let's mark off some of the interesting places. There's a local max. Here's a point of concavity change. Here's another one, so those will be inflection points. So we have here and here are inflection points. So this is minus 2 minus square root of 2. And this one here is minus 2 plus square root of 2. In the middle it's minus 2, and that's our local max, of course. It's locally the highest point. This point here is our local min. And you can see that the function is increasing here. It is then decreasing in the middle region, and then increasing again exactly as our chart said. It also has concavity going up, and then going down, and then going up again forever, which also matches our chart. So we've done pretty well, and we now have a picture that we can be proud of, and that the fact that our chart matches it means that we did the calculus correctly. And that's how you can get this sort of precise information, by using calculus.